The hypothesis space search in decision tree learning. ID3 can be characterized as searching a space of hypotheses for one that fits the training examples. ID3 will search the hypothesis space for the hypothesis which fits correctly to the training examples. The hypothesis space searched by the ID3 algorithm is the set of possible decision trees. ID3 performs a simple to complex hill climbing search through this hypothesis space. It begins with empty tree, then considering progressively more elaborate hypothesis in search of a decision tree that correctly classifies the training data. The figure shows hypothesis space search by ID3. In the figure, we can interpret the ID3 algorithm search. ID3 algorithm begins with an empty tree, then it will calculate the information gained for the attributes. This procedure will continue till we get the leaf node with the decision. ID3 capabilities and limitations. One of the capability of ID3 is ID3's hypothesis space is a complete space of finite discrete valued functions because every finite discrete valued function can be represented by some decision tree. ID3 avoids search of incomplete hypothesis space. This indicates that ID3 has got hypothesis space. In that hypothesis space, we have got hypothesis. Among them, every hypothesis will give you some decision tree. Out of them, one decision tree will be selected as the final target decision tree, which will satisfy all the training data. One of the limitation of ID3 decision tree is ID3 maintains only a single current hypothesis as it searches through the space of decision trees. This shows that ID3 does not represent all the consistent hypotheses. It determines only a single hypothesis. It does not have the ability to determine how many alternative decision trees are consistent with the available training data. The next limitation of ID3 is that ID3 in its pure form performs no backtracking in its search. Once it selects an attribute to test a particular level in the tree, it never backtracks to reconsider this choice. Once the choice is made, that is final. It cannot go back, correct it, give the other choices. This locally optimal solution may be less desirable than trees that would have been encountered along a different branch of the search. Next capability of ID3 is that ID3 uses all the training examples at each step. It makes statistically based decisions regarding how to refine its current hypothesis. The advantage is that resulting search is much less sensitive to errors. ID3 can easily extend to handle noisy training data. This is one of the best capability of ID3. Inductive bias in decision tree learning. Inductive bias is a set of assumptions together with the training data that will justify the classifications assigned by the learner to future instances. Inductive bias means giving the reason why a particular classification is made. It will give a set of assumptions together with the training data that will justify the classifications that are assigned by the learner. Given a collection of training examples, there are typically many decision trees consistent with these examples. Which of these decision trees does ID3 will choose? We need to know the ID3 search strategies. ID3 search strategy. It selects in favor of shorter trees over longer ones. It selects trees that places the attributes with highest information gain closest to the root. Approximate inductive bias of ID3. Shorter trees are preferred over larger trees. Consider an algorithm that begins with empty tree and searches breadth first through progressively more complex trees. First considering all trees of depth 1, then all trees of depth 2, and so on. Once it finds a decision tree consistent with the training data, it returns the smallest consistent tree at that search depth. Example, the trees with the fewest nodes. Let us call this breadth first search algorithm as BFS ID3. BFS ID3 finds a shortest decision tree and thus exhibits the bias called as shorter trees are preferred over longer trees. A closer approximation to the inductive bias of ID3. Shorter trees are preferred over longer trees. Trees that place high information gain attributes closer to the root are preferred over those that do not. ID3 can be viewed as compared to BFS ID3. The basic ID3 can be viewed as an efficient approximation. BFS ID3 is a greedy heuristic search. It does not conduct the entire breadth first search through the hypothesis space because basic ID3 exhibits a more complex bias than BFS ID3. Basic ID3 only concentrate on information gain. It does not always finds the shortest consistent tree. It is biased to favor the trees that places the attributes with highest information gain closer to the root. Let us find out the difference between restriction bias and preference bias. Difference between the types of inductive bias exhibited by ID3 and those by the candidate elimination algorithm. ID3 searches a complete hypothesis space, whereas the version space in candidate elimination algorithm searches an incomplete hypothesis space. In case of ID3, it searches incompletely through this space, that is hypothesis space, from simple to complex hypothesis until the termination condition is met. In case of candidate elimination algorithm, it searches the hypothesis space completely, finding every hypothesis consistent with the training data. In case of ID3, its inductive bias is solely a consequence of the ordering of the hypothesis, whereas in case of candidate elimination algorithm, its inductive bias is solely a consequence of the expressive power of its hypothesis representation. In case of ID3 hypothesis space introduces no additional bias. In case of candidate elimination algorithm also, the search strategy introduces no additional bias. Restriction biases and preference biases. The inductive bias of ID3 is a preference for certain hypotheses over others. Example, it gives preference for shorter hypothesis over longer hypothesis. This form of bias is called as preference bias, or it is also called as search bias. In case of candidate elimination algorithm, the bias of the candidate elimination algorithm is in the form of categorical restriction on the set of hypotheses considered. This form of bias is typically called as restriction bias or a language bias. If we have both preference bias and restriction bias, then which type of inductive bias is preferred in order to generalize beyond the training data, whether it is a preference bias or a restriction bias. A preference bias is more desirable than a restriction bias because it allows the learner to work within a complete hypothesis that is assured to contain the unknown target function. Means, in case of restriction bias, it will completely visits the hypothesis space. There may be a possibility that a hypothesis which will give a better solution or which will give a solution for the unknown target function, whereas in case of restriction bias that strictly limits the set of potential hypotheses, it is generally less desirable because it introduces the possibility that it may exclude the unknown target function altogether. Occam's razor. Occam's razor is the problem solving principle. It states that simplest solution tends to be the right one. When presented with the complete hypothesis to solve a problem, one should select the solution with the fewest assumptions. Occam's razor will state that prefer the simplest hypothesis that fits the training data. Why prefer short hypothesis? There are two arguments here, one in favor and one in opposition. Let us see the argument in favor. Fewer short hypotheses are preferred than the longer ones. Short hypothesis fits the training data which are less likely to be coincident. Longer hypothesis fits the training data might be coincident. Many complex hypotheses that fit the current training data but fail to generalize correctly to subsequent data. Argument in opposition. Since tree is small, hypothesis that consistent with arbitrary set of data will also be small. Occam's razor will produce two different hypotheses from the same training example when it is applied by two learners, both justifying their contradictory conclusions by Occam's razor. On this bias, we might tempted to reject the Occam's razor altogether. Issues in decision tree learning. Practical issues in decision tree learning include determining how deeply to grow the decision tree, handling the continuous attributes, choosing an appropriate attribute selection measure, handling training data with missing attribute values, handling attributes with differing costs, and improving the computational efficiency. We categorize the issues in decision tree learning with 5 points. One with avoiding the overfitting the data. In this, we will address reduced error pruning and rule post pruning, incorporating continuous valued attributes, alternative measures for selecting the attributes, handling the training examples with missing attribute values, and handling attributes with differing costs. We discuss each of these issues. We will also discuss extension to the basic ID3 algorithm that addresses them. ID3 has itself been extended to address most of these issues. With the resulting system, it is renamed as C4.5. C4.5 is the successor of ID3, which will address these issues. Avoiding overfitting the data. The ID3 decision tree algorithm grows each branch of the tree just deeply enough to perfectly classify the training examples. This is sometimes a reasonable strategy. It can lead to difficulties when there is noise in the data or when the number of training examples are too small. The algorithm, that is ID3 algorithm, can produce a tree that overfit the training examples. A hypothesis overfits the training example if some other hypothesis that fits the training example less well actually performs better over the entire distribution of the instances, that is, including instances beyond the training set. Let us see what is the definition of overfit. Given a hypothesis capital H, a hypothesis small h which belong to the hypothesis space, that is capital H, is said to overfit the training data if there exists some alternative hypothesis H dash which also belonging to the hypothesis space capital H, such that H has smaller error than H dash over the training examples, but H dash has smaller error than H over the entire distribution of the instances. We know that hypothesis space consists of all the hypotheses. Let us consider these as H1, H2, H3, or all are H and there exists one more as H dash. Now, according to the overfit definition, small h will overfit when there exists h dash in the same hypothesis space such that h has smaller error than h dash, and this is happening in training data only, whereas h dash has smaller error than h, and this is happening in training data also and testing data also, that is it is happening in the entire distribution of instances. This should not happen. That's why H is called as overfitting hypothesis. If you see the figure, it will represent the impact of overfitting in a typical application of decision tree learning. In the graph, the ID3 algorithm is applied to the task of learning which medical patients have a form of diabetes. The horizontal axis in the graph will indicate the total number of nodes in the decision tree, whereas the vertical axis will indicate the accuracy of predictions made by the tree. The solid lines will show that the accuracy of the decision tree over the training examples. The broken lines or dotted lines will show the accuracy measured over an independent set of test examples. The accuracy of the tree over the training examples increases gradually as the tree grows. However, the accuracy measured over the independent test examples shown by dotted lines first increases, then it will decrease. Once the tree exceeds approximately 25 nodes, the tree decreases its accuracy over the test examples despite increasing its accuracy on the training examples. How it can be possible for tree H to fit the training example better than H dash, but for small h to perform more poorly over subsequent examples? One way this can occur is when the training example contain random errors or noise. To illustrate this, consider the effect of adding one positive training example incorrectly labeled as negative to the example which we have considered earlier, that is play tennis example. Given the original error-free data, ID3 produces the decision tree as shown in the figure. However, the addition of this incorrect example will now cause the ID3 to construct a more complex tree. This is shown in the figure. In particular, the new example will sorted into the second leaf node from the left in the learned tree of the figure shown, along with previous positive examples D9 and D11. Because the new example is labeled as negative example, ID3 will search for further refinements to the tree below this node. As long as the new erroneous example differs in some arbitrary way from the other example affiliated to this node, ID3 will succeed in finding a new decision attribute to separate out this new example from the two previous positive examples at this tree node. The result is that ID3 will output a decision tree that is more complex than the original tree. small h will fit the collection of training examples perfectly, whereas the simpler h dash will not. However, given that the new decision node is simply a consequence of fitting the noisy training example, we expect small h to outperform the small h dash over the subsequent data drawn from the same instant distribution, because h dash is addressing all the training examples and testing examples. This example will illustrate how random noise in the training example can lead to overfitting. In fact, overfitting is possible even when the training data are noise free, especially when small number of examples are associated with the leaf nodes. In this case, it is quite possible for the coincidental regularities to occur. Overfitting is a significant practical difficulty for decision tree learning and many other learning methods. There are several approaches to avoid the overfitting in decision tree learning. These can be grouped into two classes: approaches that stop the growing tree earlier before it reaches the point where it perfectly classifies the training data, and approaches that will allow the tree to overfit the data and then post prune the tree. Approaches to avoiding overfitting in decision tree learning: pre pruning and post pruning. Pre pruning is the avoidance stage. It will stop growing the tree earlier before it reaches the point where it perfectly classifies the training data. Whereas post pruning is the recovery stage. It allows the tree to overfit the data and then post prune the tree. Criteria used to determine the correct final tree size. For post pruning, we use a separate set of examples which are distinct from the training examples. It produces an improvement beyond the training set. We use measures of the complexity for encoding the training examples and decision tree, halting the growth of the tree when this encoding size is minimized. Means we will stop the growing of the tree when the encoding size is minimized. This approach is called as minimum description length, MDL. So MDL will minimize the size of the tree and size of the misclassification of the tree. Reduced error pruning. Reduced error pruning is to consider each of the nodes in the tree to be a candidate for pruning. Pruning a node consists of removing the tree rooted at that node, making it a leaf node, and assigning it the most common classification of the training examples. Nodes are removed only if the resulting pruned tree performs no worse than the original over the validation set. After applying the reduced error pruning, we will get the graph as shown in the figure. The impact of reduced error pruning on the accuracy of the decision tree is shown in the figure. Compare this graph with the earlier graph which is shown. You can notice the accuracy which was drastically reducing after the size of 25 reducing at a faster rate on test data during the error pruning. The available data has been split into three subsets: the training examples, the validation examples used for pruning the tree, and a set of test examples. What are the pros and cons of this method? The pros are it produces smallest tree of most accurate tree, that is subtree of capital T. The con side is it uses less data to construct the main tree. Can it afford to hold out the validation data only? If not, it may make error worse, that is insufficient training data. That is treated as the con side of this method. Rule post pruning. Rule post pruning is successful method for finding high accuracy hypothesis. Rule post pruning involves the following steps. Infer the decision tree from the training set, allowing overfitting to occur. Convert the learned tree into an equivalent set of rules. One rule for each path from the root node to the leaf node. Prune each rule by removing any preconditions that result in improving its estimated accuracy. Sort the pruned rules by their estimated accuracy and consider them in this sequence when classifying the subsequent instances. The figure will show the converting of a decision tree into rules. Here we will apply if with AND function. For example, if we consider the left path, then it is if outlook is equal to sunny and humidity is equal to high, then play tennis is no. One more path may be if outlook is equal to sunny and humidity is equal to normal, then play tennis is equal to yes. Like this, all the rules are taken out from the decision tree. In short, the decision tree is now converted into a set of rules and each rule is pruned. There are three main advantages by converting the decision tree to rules before pruning. The pruning decision can be made differently for each path. By looking at the path, we may consider changing the attribute values to reach to a better efficiency. Converting the rules removes the distinction between the attribute tests that occur near the root and the leaves. If at all we consider different decisions or we have modified, definitely the root and the leaves may change. Converting to rules removes the distinction between attribute tests that occur near the root and leaves. Thus, it avoids messy bookkeeping issues. Converting to rules improves the readability. Users can understand more easily these rules. Rules are often easier to understand. Incorporating continuous valued attributes. Continuous valued attributes can be incorporated into the learned tree. There are two methods for handling the continuous attributes. First one is define new attributes that partition the continuous attribute values into a set of intervals. For example, suppose that the value of the attribute is lying between 10 degrees to 35 degrees. This can be converted into continuous attributes with the values high is equal to temperature greater than 35 degrees centigrade, medium is equal to temperature between 10 degrees and 35 degrees, low is equal to temperature with less than 10 degrees centigrade. Or we can adopt to the second method, that is using our own thresholds for splitting the nodes. Alternative measures for selecting the attributes. The problem is if attributes with many values, gain will select which one of them. Example, consider the attribute date, which has a very large number of possible values. For example, March 4, 1979. In this case, the values are March is one, 4 is another, and 1979 is one more. If this is the case, then GAIN will accurately classify the training data because it is a very precise data. Suppose that the decision tree has made date as the root. We see that it is not a useful predictor because it perfectly separates the training data, but it poorly predicts the subsequent examples. One approach is to use the gain ratio instead of gain, that is information gain. The gain ratio formula is gain ratio of the sample for the attribute is equal to gain of the sample for the attribute divided by split information for that attribute. Split information of the sample for the given attribute is minus summation of probability of the sample considered, log to the base 2, and probability of that sample. Handling the training examples with missing attribute values. The data which is available may contain missing values for some attributes. One example is shown. Fever is equal to true, blood pressure is equal to normal, but blood test value is missing. Sometimes values are truly unknown. Sometimes it is given very low priority, or finding out that value will cost very high. If we consider the play tennis example, we may find one missing data. For example, in 8th row, the humidity attribute value is missing. Strategies for dealing with the missing attribute values. If node n test A assign most common value of A among other training examples sorted to node n, assign the most common value of A among other training examples with same target value. Means we are considering the other training examples in that attribute and we are assigning the similar value over there. Assign a probability Pi to each of the possible values Vi of A rather than simply assigning the most common values to A of X. Means we directly won't substitute the most common value. Instead of that one, we will calculate the probability of the possible values of that attribute. Handling the attributes with differing costs. In some learning tasks, the instance attributes may leave associated cost. For example, in learning to classify medical diseases, the patient described in terms of attributes such as temperature, biopsy result, pulse, blood test results, etc. These attributes vary significantly in their cost, both in terms of monetary cost and cost to patient comfort. Decision tree use low cost attribute where possible, depends only on high cost attributes only when needed to produce reliable classification. Means decision tree will consider low cost attributes and can neglect the high cost attributes when it is necessary. How to learn a consistent tree with low expected cost? One approach is replace gain by cost normalized gain. This is given by tan and skimmer. The formula is gain square of the sample for that attribute divided by cost of that attribute, or we can use Non's formula which is given by 2 raised to gain of the sample for that attribute minus 1 divided by cost of that attribute plus 1 raised to omega, where omega is 0 or 1, which determines the importance of the cost.